All right, so this chapter, Module 8, is going to go over the VPN IPsec concepts. We're going to describe the different types of VPNs that are out there and then what they bring to us as a organization. So how are the VPNs and IPsec used to secure site-to-site and remote access connectivity? We're going to describe the benefits of this and the types of VPNs that are out there, who manages them, and how we implement them, and exactly how the IPsec framework is used to secure this traffic. So VPN technologies. So a virtual private network basically allows us to create end-to-end connections that are encrypted across public office space. So VPN is a virtual connection within the private networks that allows information to flow over public networks or the internet. The VPN is also private in that we use encryption to keep the data confidential while we're transporting it over the public network. So what would be the benefit of using VPN? Well, for one, it brings the IPsec and secure socket layers into play so we can secure our data from remote to internal, or from two remote sites that need to be able to communicate with one another. And by doing this and being able to use the public internet connections and bandwidth that's available that can be cheaper, it allows us to save money. So we can use these VPNs to reduce our cost. Whereas before, if I had 5 locations, for all 5 locations to connect up to each other, I would have to have 5 different connections at each site. And a connection can vary in cost from, a couple $100 upwards of thousands per connection. So you're talking about 5,000 times 5. It's a lot of money on a monthly basis to outlay. The other thing that this brings into play is that we can use security or encryption to protect our data and make sure it's not compromised, and it gives us the ability to grow or scale. VPNs can be implemented across a wide variety of WAN links, so we're not strictly tied to coax as a provider or AT&T fiber. We can use different ISPs and different connection types and all intermingle. So we're highly capable when we move to a VPN technology. One of the ways that the VPN technology can be used is for site-to-site and remote access. So when we have a sales rep that's at a hotel that needs to turn his cells in at the corporate office for the day, he can use a client application to make a site-to-site connection and dump the data onto our servers. Or if we have 2 offices at separate locations that are remote with public network connections, we can set up an encrypted tunnel that's always on to allow us to dump information in. So make sure you're aware here that when we're using this example, that this is a router to router or ASA to ASA or some firewall appliance talking to another firewall appliance to set up this tunnel. Here our end user uses a piece of software called a VPN client to establish a connection to the firewall. Still gets the same access. We still have the same encryption and security. It's just now that we have a 2-factor authentication method needed to work with our software that's on a actual endpoint or device. So here's some differences. As an enterprise, we can actually buy and own the equipment necessary to set up site-to-site or remote access VPNs within our organization. We are our own customer, and we are managing our own devices. So all we're looking for from the provider would be some form of connection or bandwidth. And then on the flip side, we can also use the service provider themselves to provide us all the equipment and the appropriate protocols. So in here, one of the newest technologies out there is MPLS. And you can see that the service provider, AT&T, C-Spire, Sprint, Verizon, any of your service providers, can be used to manage and provide us this end-to-end connection between our offices. So you can see that over here in the service provider slide, the layer 2 MPLS, layer 3 MPLS is controlled by that ISP. An old solution with less secure methods that we used for point-to-point or office-to-office connections was frame relay, and after frame relay came ATM. Again, ATM is pretty much being replaced by MPLS these days. We've already discussed some of these, but we're going to go ahead and highlight the different types of VPNs. So again, we have client lists. So this means that we have a remote device or endpoint, a tablet, iPad, computer with a browser. And so if we didn't want to install software in our devices and we wanted to provide access, if our firewall appliance or firewall allows this, we can actually use SSL and a web browser to make a connection to our remote office. The other way we can do is actually install software. If we're doing Cisco devices, they use something called Cisco AnyConnect, a secure mobile client that we would install on the tablets or PCs that are to be used for remote connections to our headquarter office. So an actual application is required. Some firewalls support two-factor for their VPNs, some don't when we get into the clients. So that's another aspect. If that's required, you need to make sure that your hardware can handle. And again, VPNs with SSL tech can be used and established via a web browser. And then IPsec or SSL can be used to establish connections with a client application provided by your firewall manufacturer. I'm going to highlight this. So with SSL, we have to actually have a certificate that can be publicly purchased, or we can use a factory installed certificate that we generate at the actual appliance. Most of the time I see the actual factory appliance certificate being used. The type of method that is used or is based on the access requirements of the users and organizations, IT. This table compares some different ones. So you can see applications supported for IPsec is extensive. So this runs over all IP-based applications. SSL is limiting. It's only a web-based application and file sharing medium. When we get into the authentication, this is a two-way handshake that we can encrypt and share our keys and certificates to make sure that we don't have problems. You can see that it's a strong authentication method with IPsec, and with SSL it's a moderate one or two-way authentication mechanism. So authentication and encryption are two different things. You can see in the encryption we can use a strong key with lengths of 56 to 256 bits or higher when it comes to IPsec. And we can use a moderate to strong key of 40 to 256 bits with SSL. So just so you're aware, when we talk about the encryption, there are actually, with the newer appliances, with what we have in today's environment, a lot of different mechanisms and methods. So it used to be it was all MD5 or another weak one, DES. So DES is a 56-bit encryption key. It was replaced by triple DES, which I think got us to 256. Now more modern devices let us go up way higher, I think 2048 or more, and they're using AES. So we actually have like 3 different encryption methods that we can use for setting up VPNs on a more up-to-date appliance. The complexity is going to be dependent on the environment. It's a medium requirement with IPsec, and it's very low connectivity situation when we talk about the browser. So site-to-site is going to be using IPsec only. These are, well, I say that, unless you were using a Cisco GRE, which, unless you add something to it, doesn't have encryption. So Cisco has an end-to-end between routers called GRE that we need to know about. But as far as setting up a tunnel between 2 locations, if it's appliance to appliance, we're going to use IPsec. So end hosts send and receive normal unencrypted TCP/IP traffic through the VPN gateway when they're just going out to the public, untrusted stuff. When we're actually moving data between one private network and the other, the VPN gateway encapsulates and encrypts all this traffic. It has to go through the tunnel, and it makes sure that it gets securely delivered to the other side. So this is the GRE that we were talking about. That's a Cisco item. The generic routing encapsulation is a non-secure site-to-site VPN tunnel. So this is basically a tunnel that we're allowed to do with Cisco equipment between routers so that we can move data from one private network across a public network to another private network. It encapsulates the network layer protocols as well as multicast and broadcast. It does not default support encryption, and therefore it does not provide a true secure tunnel. We have to add something to it to make it secure. A GRE packet can be encapsulated into an IPsec packet to forward it securely. So you would add IPsec to encrypt and secure GRE. Standard IPsec VPNs, non-GRE, can only create secure tunnels for unicast traffic. So if we wanted to remove the encryption and set up a tunnel across a public, we can use Cisco equipment and do so using GRE. We can also add IPsec to GRE to make it more secure. So GRE in the terms described, again, encapsulates our protocols, but allows us to add IPsec if we want to secure it. So you can see that they have a transport layer protocol here. In IPsec VPN or GRE over IPsec is to support the routing traffic from one site to another. Specifically, OSPF passenger would be encapsulated by GRE, subsequently encapsulated in IPsec VPN tunnel. So you can see that they've got multiple things going on here, two different tunnels to protect our GRE, which is a router-to-router mechanism. Site-to-site IPsec VPNs and GRE over IPsec are not sufficient when the enterprise adds many more sites. A dynamic multi-point VPN would be required. A Cisco software solution for building multiple VPNs is an easy, dynamic, and scalable manner. So DMVPN, which is Cisco's version of MPLS basically, simplifies the tunnel configuration and provides a more flexible option to connect the central site with branch sites. This thing uses a hub and spoke, so our headquarters down to all our remote sites to establish a full mesh topology. Spoke sites are required to establish secure tunnels with the hub site. Each site is configured using multi-point generic routing encapsulation. Again, this is a Cisco thing. The MGRE tunnel interface allows a single GRE interface to dynamically support these tunnels. Spoke sites can also obtain information about each other and alternatively build direct tunnels between themselves. So IPsec virtual tunnel interfaces are used to simplify our config process required to support multiple sites and remote access. IPsec VTI configurations are applied to a virtual interface instead of a static mapping in these IPsec sessions to a physical interface. VTIs are capable of sending and receiving both IP unicast and multicast encrypted traffic. Therefore, routing protocols are automatically supported without having to configure GRE tunnels. IPsec VTI can be configured between sites or in a hub and spoke topology. Again, I'm going to highlight that today service providers use MPLS and allow the ISP to help or assist with the core network that is forwarding traffic. This MPLS backbone uses labels and is secure because the service provider customers cannot see each other's traffic. We can only see our own. So MPLS can provide clients with managed VPN solutions, therefore securing traffic between our sites, and is the responsibility of our service provider. Again, AT&T, Comcast, whoever is providing the MPLS VPN connection. These things can function at both layer 3 and layer 2. So at layer 3 VPN, the service provider participates in customer routing by establishing a peering between the customer's routers and the provider's routers. And at layer 2, the secure provider is not involved in the customer routing. Instead, the provider just deploys a virtual private LAN, VPLS, to emulate an Ethernet multi-access segment over our network. So no routing is involved. The customer's routers will effectively belong to the same access network. So what is IPsec and how do we use it? We're going to cover this in a separate video. So IPsec was developed by the IETF like a lot of other standards. This is the Internet Engineering Task Force. It defines how VPN can be secured across IP networks. IPsec is used to protect and authenticate our packets between source and destination. So it provides all of these functions. Confidentiality, so encryption algorithm to prevent cyber criminals from reading our packets and data. Integrity, we use hashing algorithms to ensure that the packets haven't been altered during transportation. So we make sure that if it's coming from a source and received by a destination, that it actually came from the source. We have Internet Key Exchange, or IKE protocol, version 1 or 2, used for authentication, source, and destination. And we use Diffie-Hellman to secure our key exchange. IPsec is not bound to any specific rules for communications. It can easily integrate new security technologies without updating existing standards. The open slots in the IPsec framework shown in the figure can be filled with any of the choices that are available for that IPsec function to create a unique security association. Choosing the IPsec protocol encapsulation is the first building block of our framework. So this determines the authentication header or encapsulation protocol, ESP. The choice of AH or ESP establishes which other building blocks will be available. So AH is appropriately only when confidentiality is not required or permitted. ESP provides both confidentiality and authentication. The degree of confidentiality depends on the encryption algorithm and the length of the key used in the algorithm. So the number of possibilities to try to hack the key is a function of the length of the key. The shorter the key, the easier it is to break. So if we're using DES and a 56-bit key versus AES and a 2048-bit key, there's a big difference in the time required to get into the hashes. So here's some of the highlighted keys that are out there. So all these are symmetric. So we have DES uses a 56-bit. Triple DES is 3 times 56. Encryption keys are in a per 64-bit block. Then we have AES offering 3 different lengths, which are actually more than that now: 128, 192, and 256. Then we have something called SIL, which is a stream cipher, which means it encrypts data continuously rather than encrypting blocks of data. It uses a 160-bit key to do so. Data integrity means that the data has not changed in transit, and so we're going to have some form of hashed message authentication to verify the integrity of the data that hasn't changed. So MD5 and SHA are the 2 most common that I see that are currently used within VPN technologies. So there are 2 IPsec pure authentication methods. One, a PSK or pre-shared key, so basically a password we enter on both sides of the firewall. Most of the time when we do this method, we actually exchange the key verbally over a phone, write it down and key it in. That way we're not passing in some mechanism to where we have to worry about the key getting hacked or compromised. Or we can use RSA certificates. We can use digital certificates that are locked down at each side, and then we pass the information required for each peer to be put on their end so we can encrypt data back and forth. RSA can be used for things like SSH and other technologies as well. So the Diffie-Hellman provides us to allow 2 peers to establish a shared secret over an insecure channel. So you got multiple different DH groups out there. 1, 2, and 5 should no longer be used. We are moving up to DH groups 14, 15, and 16, which use larger key sizes, 2848 up to 4096. And then we can go even farther with Diffie-Hellman 19, 20, 21, 24, where you can see that we have an elliptical crypto curve of 2048. Reduces the time needed to generate these keys. And then there's another video out there for you guys to explore on IPv4 packets and the transportation of ESP. We're done with Module 8. I'm going to build a separate video that kind of shows you how to set up an IPsec site-to-site VPN and see it in operation, as well as a client-based VPN. There's all different forms and fashions of configs, some more advanced than others. So I just want you guys to be aware and see the actual configurations.